to those in China and the countries around. And good morning to the rest of the world. My name is Joseph Jonathan Magoua from Tsinghua University. And today I'll be presenting my study titled Towards an HLA-based Modeling of Interdependent Infrastructure Systems. So the content of my presentation today will cover the background, motivation, methodology of my study, and I'll conclude with a case study and practical applications. Infrastructure systems such as transportation, water, power systems are the backbone of urban societies. They provide the basic needs and services necessary to sustain daily activities of citizens and also to ensure economic growth and sustainable development of the built environment. However, these systems are not independent, but rather they rely on each other to ensure their proper operations. And the interdependencies between these infrastructure systems give rise to several problems or challenges. For example, interdependencies increase the vulnerability of infrastructure systems and facilitates the propagation of the impact of disruptions or disasters in the system. Prior studies have attempted to address these challenges by proposing different approaches to model and study infrastructure systems. For example, network-based modeling, agent-based modeling, system dynamics modeling. Although these systems, although these approaches are able to represent the systems and their functionalities, but they only present a highly abstracted representation of the topology and the functionalities of the systems, leading to limited ability to capture systemic heterogeneities among the systems and their components, and also provide insufficient consideration of the functional interdependencies between the systems. These limitations can be well addressed by using domain-specific models. These are physics-based models that leverage the knowledge, data, and techniques that have been accumulated over several years of research in the individual infrastructure system domains. So basically, our study aims at proposing a framework that can integrate multiple fine-grained infrastructure domain-specific models to develop more detailed, improved, and realistic interdependent infrastructure systems models. But one problem arises due to the fact that these domain-specific models have been developed independently of each other based on equations, algorithms, and physics that are specific to individual infrastructure systems, so they cannot be simply linked together. There arises issues of interoperability due to the heterogeneous nature of the models, the data, and the simulation tools. So to address this problem of interoperability, we decided to adopt a high-level architecture-based co-simulation technique. HLA is a widely adopted standard for developing co-simulation platforms that offer several advantages, including interoperability of heterogeneous models and data, reusability and extendability of federations, and also security to the modelers and to their data. So based on the HLA standards, we proposed an HLA-based framework for modeling interdependent infrastructure systems. Just as the figure here presents, the architecture of this federation is composed of several critical infrastructure system modules. Each module consists of the domain-specific models that are responsible to model the dynamic evolutionary state and behavior of the infrastructure systems, and a DPU, which is a data processing unit that manages the data exchange between the different domain-specific models so as to model the interdependencies between them. And at the center of this architecture, we have the RTI, the Runtime Infrastructure Middleware, that provides the federation with data exchange and synchronization services. And the architecture also has other modules, such as the user module, which consists of graphical user interfaces, data monitors that facilitates the interaction between the federation users and the federation, and also an external environment module that consists of disaster simulators, human decision models, and so on and so forth. The data exchange and data processing mechanism of the federation is modeled in the form of publishing and subscription of data between the domain-specific models. And the subscribed data is processed by means of dependency functions to obtain an input, which can be assimilated by the domain-specific models. So this is the overall framework that we proposed. Now, to test the effectiveness of our framework and to validate the framework, we conducted a case study of the infrastructure network of Shelby County, Tennessee, in the United States, which has a population of about 940,000 people and a surface area of 784 square miles, which is a significantly large-scale network of infrastructure systems. And we focused on the interdependent power and water systems. The power network consisted of 8 generators and 17 substations connected with a wide network of transmission lines, and a water network consisting of 9 pump stations, 6 tanks, and 43 junctions. The figures below show a layout of the components of these systems on the map of the Shelby County. Then to model our systems, like we said, we used wide models, which are physics-driven models. For example, for the water systems, we adopted the pressure-driven hydraulic analysis model, and we used the EPANET API simulation tool for simulation purpose. And for the power system, we adopted the power flow analysis model, and we simulated it using an OpenDSS API package. So our our interdependent infrastructure systems model was simulated under normal operational conditions for a simulation duration of 48 hours. And the conditions of the simulation was set in such a way that the demand in the water system could alternate based on a typical urban water demand pattern, whereas in the power system, the demand was fixed. The reason for doing so was to be able to observe how the dynamics within one system could affect the functions or the behavior of the interdependent system. And by so doing, we will be able to validate and verify that our framework is able to actually simulate interdependent systems and the interdependencies between them. On the figure on the top left here, it presents the layout of our federation. So we implemented this federation on 2 separate computer hardware. One computer hosted the water supply system, and the other computer hosted the power supply system. And the 2 computers were connected via a local access network. On the right, we have a table of all the objects, entities, and attributes for the 2 interdependent systems. And this shows the level of detail and granularity that our models were able to achieve. And on the bottom left, the figure here shows the actual data that was exchanged between the models. For example, you can see the water system could publish information about pump statuses, power consumption of the pumps, and whereas the power system could publish information about the actual power output to each of the components in the interdependent system. So coming down to the simulation results, the results demonstrated that the proposed framework is able to provide detailed simulation of the evolutionary states and behavior of the systems at a component level, which is very important, component level, rather than system level like prior approaches. For example, here, the changes in the demand was able to affect different metrics within the water system or affect the behavior of different components within the water system. And these behavior can be traced, can be detailedly traced and analyzed for other purposes. Secondly, the developed model was able to capture the interdependent effect. That means the intra and inter-system influence paths and mechanisms could be observed. For example, the changes in water pressure were controlled by the operational statuses of the pumps within the water system. And then we are able to also model how the changes or the dynamic processes happening within the water system are going to affect the power system, since the power system was responsible to supply power to the pumps within the water system. And finally, the simulation results also help to identify vulnerabilities in system design and operational processes. For example, in the figure here, we are able to identify some stability issues in the water pressure within the water network due to the closure of certain pump stations. And this may indicate faulty design of the water distribution network, which are later improved or solved. So our study provides a significant contribution to the area of infrastructure systems management in two ways. The first is that it contributes to component level vulnerability analysis of infrastructure systems, thanks to its high granularity and details of the models and simulation results. And also the dynamic fine-grained simulation environment provides more information for the detailed assessment of system resilience, and also the assessment of the efficacy of resilient improvement measures. So this brings me to the end of my presentation today, and I will be glad to answer any questions that would come up. Thank you.
Thank you. Thank you, Jonathan.